This is part 2 of the lecture. In the previous part, we developed a model from scratch in an Excel spreadsheet using this model structure. We calculated runoff, and now we want to evaluate our model and estimate our parameters. As I mentioned earlier, we have some performance metrics, Nash-Sutcliffe coefficient, for example, and error. Now we want to use these performance metrics to evaluate our model. If you're not familiar with performance metrics, or if you don't know what is Nash-Sutcliffe coefficient, please review hydrology textbooks. In this lecture, we focus on modeling. I'm not covering fundamentals of hydrology, but briefly, Nash-Sutcliffe coefficient, along with other metrics, are widely used in hydrology to evaluate simulations relative to observations. Here you can see the equation for Nash-Sutcliffe coefficient. QS is Q simulations minus observations. And here the denominator is observations minus long-term mean of the observations. The upper bound of Nash-Sutcliffe coefficient is 1. That's when this term is 0. It means simulations and observations are the same. And the lower bound is minus infinity. If Nash-Sutcliffe coefficient is less than 0, it means the model has no predictive power. It simply means that long-term average of observations is better than our model. So our model is pretty useless. Back to our simulations versus observations. There are different sources of error. For example, error in initial conditions. We used initial values for soil moisture, snow, storage 1, and storage 2. You may have real observations from your field. Like, for example, 25 millimeters of snow on the ground could be based on real observations. In that case, then the error is probably small. It's only related to measurement, but you may not have any information at all. My study area is a basin in Europe, and I'm starting in January. So I assume there is snow on the ground. It's not an unreasonable assumption. In fact, it is very reasonable, but I don't know how much. I use 25. And this has some implication, and we will talk about that later. Also, for soil moisture, we always have to assume there is some moisture in the soil, but in reality, we may not have any observations. So there is some error from initial conditions. Then there are also errors related to model structure. These model structural errors are hard to evaluate, but we know they are there. We made a lot of assumptions. For example, we assumed that outflows from our bucket models are simple linear functions. Outflow is a function of storage. The whole bucket model itself is a very simple representation of really complex processes. So we made, a lot of assumptions. So these assumptions contribute to the overall error. These errors are related to the way we define the model and a little hard to quantify. But there are methods already designed to evaluate model structural errors, and you can review the literature to learn more. There are also errors in our observations, input precipitation, temperature, and also discharge data that we use for evaluation. There are also methods in the literature that focus on input uncertainty, and more importantly, model parameters. Our model has 10 parameters, and we just simply assumed some values, hopefully reasonable values, but we know that they are not perfect, and we have to go back and adjust them. Here, we don't talk about model structural errors and input uncertainty. Those are topics that you can learn in the literature. We focus mainly on initial values and model parameters. Initial values in our model are the 4 variables snow, soil moisture, S1 and S2. In other models, you may have different initial values. These are the variables we used in our model, and there are 10 parameters for describing the underlying processes. Let's start with model parameters. Here I am putting them in 2 different categories. All of my parameters are conceptual. They are designed for the conceptual model I developed. But some of them are more physically based. They are measurable in the field. For example, field capacity. You can take a sample from the study area and estimate its capacity to hold water. Degree day factor also is measurable. Permanent wilting point and temperature threshold are also similar. So these are parameters that you may be able to actually measure if you have time and resources. There are some other parameters that are not physically based, or at least not easily measurable. Beta is one of those. It serves as a knob in our model. It allows us to control how much water goes into the system, but it doesn't have any physical meaning and you can't really measure it in the field. K parameters are more related to soil properties. So you could argue that they could be measured somehow. They describe delays and retention in the system, but again, those are not easily measurable, so I put them in purely conceptual category. If I can make reasonable assumption for my measurable parameters, I work with conceptual ones. I try to improve my model only with those parameters, and if it didn't work, I will add more parameters from the second category. But there are different strategies out there. You can try to calibrate all of them at the same time. It depends on what method you're using for calibration and parameter estimation and what's your main objective. But in most cases, we try to estimate all parameters. We developed the model in an Excel spreadsheet, and here we have limited options for model parameter estimation. We use Solver, which has its own limitations, but at least it allows us to randomly change parameters and improve the model based on an objective function. If you don't have Solver, go to Add-ins, Solver, click on OK. Then you should be able to find it here. So here you can select your objective function. For example, maximizing Nash-Sutcliffe coefficient. Remember, the upper bound of Nash-Sutcliffe coefficient is 1, so you may want to maximize it. Or minimizing your error. If error is based on absolute values and lower bound is 0, then you can minimize your error or make it equal to 0. If your objective function is root mean square error, again, you can minimize that objective function. Let's quickly calculate Nash-Sutcliffe coefficient. Here are the two terms. First, we calculate this part in the Excel spreadsheet. Then the denominator, Q observations, minus long-term mean of the observations. The long-term mean is already calculated. Now you can see the Nash-Sutcliffe coefficient is very low and our error is very high. So this model is not good. You're going to use a simple optimization tool to estimate the parameters and improve the model. To start Solver, let's start with error as our objective function. Our goal is to make error as close to 0 as possible. So we pick F21 or error as our main objective function. It is now 28%. We want to bring it down to 0 or as close to 0 as possible. Then these cells are the parameters I have selected for optimization. As you can see, I have not included all of them. Like temperature threshold is not included here. You can use all the parameters or some of them. Here for simplicity, I'm using some of the parameters, the ones that are more important. We talk about parameter sensitivity in a moment. In most applications, we want to estimate all of our parameters. Here, I've added some constraints. Remember that PWP has to be less than field capacity. That's how we defined it. So we have to make sure that through this optimization process, parameter estimation, PWP remains less than field capacity at all times. We also talked about K parameters in the previous lecture, and ideally, we we want K0 to be larger than K1, larger than K2. So you can add those conditions here. For example, field capacity is column C11 and PWP is F13. You can see here, one of the constraints is PWP less or equal to field capacity. This constraint makes sure that PWP remains less than field capacity. Here in options, you can increase the number of iterations. The default is 100. When you have this many parameters, 100 is small. You need more iterations. But for now, just so that we get a quick answer, I don't increase it. The optimization part is done. As you can see, the error is now, it's almost zero. But our nice Sutcliffe coefficient has not improved. In fact, it is still really, really bad. You can see that the model changed some of our parameters and initial assumptions. For example, initial value of beta was 1. It is now in the updated set is 4.2. Our error is 0, but our nice Sutcliffe coefficient is far from ideal. The reason is error, the way we have defined it, is not a suitable overall objective function. So it's really important to find the right objective function for model calibration or parameter estimation. So imagine observations and simulations in this form. Here, the sum of the two could be similar and the overall error could be very small. But as you can see here, observations and simulations are very different. In that case, error is not a good objective function to describe model performance. We need something else. Now, let's try nice Sutcliffe coefficient as our objective function. We go to solver again. This time we use nice Sutcliffe coefficient, F27, as our objective function. Our goal is to maximize nice Sutcliffe coefficient. Remember, the upper bound is 1, and 1 is ideal for us. We change these parameters, and constraints remain the same. We have to wait until all the iterations are done. Again, I'm using the default 100. In practice, you need to use a lot more. Now we see that nice Sutcliffe coefficient has improved. It is 0.48. It is still relatively low. Beta increased to 5 and correlation coefficient around 0.7. Now we can make some changes, start with different initial values. Let's say initial value of field capacity of 180. If you change the parameters, the starting values for iterations also change. So you will end up with different overall error and nice Sutcliffe coefficient because there is a lot of random sampling involved. I run the solver again. In this round, our best beta is 6.1 and our nice Sutcliffe coefficient 0.71. Now we made a huge improvement in nice Sutcliffe coefficient from the first try 0, close to 0, to the second try 0.48, and in this try with 1000 iterations and a different set of parameters 0.71, which is pretty good. Now let's briefly talk about parameter sensitivity. This deserves a lecture on its own, but I want to briefly highlight that not all parameters are equal when it comes to model performance. If you use your Excel spreadsheet and you change parameters one at a time, for example, beta, you can see that error will change significantly. We can look at nice Sutcliffe if you want. But in here, we are looking at error in the y-axis and different beta values. So basically, I use beta of 1. I noticed the error was 30%. 2, error dropped to around 15%. 3, 5%. Then there is a value that gives you kind of the lowest error, and after that, error increases. You can do the same with nice Sutcliffe coefficient. This shows that my optimal value of beta is somewhere around 5. This means that with a very little change in beta, like from 1 to 2, error changes significantly. This means that the model is very sensitive to this parameter. Now let's do exactly the same thing with degree day factor. So again, I changed degree day factor from 1 to 2, 3, 4, 5, and I looked at the error. Error changes, but changes are very small. This means that if I compare these two parameters together, beta and degree day factor, my model is very sensitive to beta, but it is not very sensitive to degree day factor. And it kind of makes sense. Degree day factor only affects days that you have snow on the ground, but beta basically changes your effective precipitation, the amount of water that contributes to direct runoff. So beta is more sensitive. If I'm doing calibration, I definitely should include beta. I cannot ignore beta at all. In this particular case, I ignored degree day factor, and my overall performance was not bad. Now, I'm not saying that we should not include degree day factor in calibration and parameter estimation. In fact, I think we should do this, but I just wanted to make a point that in this case, if there is a very big difference in sensitivity, we can focus on the ones that the model is more sensitive to. They may be enough to get really reasonable simulations. If not, of course, we can go back to less sensitive models and bring them in. The other important issue is that parameters sometimes interact with each other. This is a simple experiment when you change one parameter at a time. In reality, when you change multiple parameters at the same time, then your results will be very different. We talked about model parameters. Now let's talk about our initial values. Remember, we made some assumptions, like there is 100 millimeter equivalent of soil moisture, and we want to go back and revisit our assumptions. These are the initial values we used. Let's start with soil moisture. How about we do a simple experiment? We go back into our Excel spreadsheet and we simply change our initial value and look at the performance. Let's look at my nice subcliffe coefficient here, or error. Now let me increase 100 to 200. That means a huge change, like 100% error. Instead of 100, 200. If I look at my nice subcliffe coefficient, you see that it remains the same. But why? Now here, I have done the same. Instead of 100, I used 125, 150, 75, and 50. And I'm looking at soil moisture time series. So you can plot soil moisture time series and look at it over time. And I'm just zooming into the first 300 days. You have 10 years of data, so you simulated 10 years of soil moisture, but I'm just looking at the first 300 days. As you can see, no matter where you start, they all converge together at some point. Here, in around 70 or 80 days, all these lines converge together. And after that, it basically doesn't matter what initial value you used. We call the time that it takes all these initial values to converge together as memory of the model. After a while, the model forgets about the initial values because there are other processes and variables that interact with each other. And after a while, the initial value effect is very, very small. This means that initial values are important at the beginning of the simulation for a certain period of time. How long depends on the model, number of parameters you use, processes you have simulated, and you can easily test this. Change your initial values and look at those time series and see what's the memory of the system for that particular parameter. If you do long-term simulations, like for example 10 years in our model, error is very small, as you can see here. But if you're doing short-term simulations, if you're simulating 100 days only, that's what you care about, you only want to do 100 days of simulations, then the effect of initial values are very significant. This means that if our objective is long-term simulations, we don't have to worry too much about initial values. We can simply ignore them or remove the first, let's say, 100 days or the first 50 days, depending on the memory, and just work with the rest. But for short-term simulations, the initial values are very sensitive. We cannot simply ignore their impacts. There are different strategies to find a good initial value. One option is to treat them like other model parameters and try to calibrate them. That's one way. Of course, not everyone agrees that's a good idea, and I'm not suggesting we should do that, but if we cannot improve the model based on parameters, we may want to try bringing in initial values like parameters and try to improve the model overall with both parameters and initial values as changing variables. The same model we talked about is also available in Matlab. You can download it from my website. It's available with a graphical user interface. Here you can load your data and run the model. The source code is also available for those who want to make changes or integrate the model into their own workflow. The model has the same parameters, degree, day factor, field capacity, and so forth. The difference is here for each parameter, we have a lower bound and an upper bound. In Excel spreadsheet, we did not have this option. We relied on the random sampling scheme built into Excel. But here we use Monte Carlo simulations, and you can set a lower bound and an upper bound for each parameter. It means you tell the model to sample randomly between these values for each parameter. The model will then search for the best set of parameters, and for each parameter, you get the optimal value here. Initial values are included here. You can load your input precipitation and temperature data. The package comes with sample input data, same data available in the Excel spreadsheet. If you want to load your own data, make sure that you format your input precipitation and data like the one sample provided. You need to load your monthly temperature and monthly evapotranspiration. And also you need to have observed discharge for parameter estimation. For all of them, you have sample data in the package. You can select your optimization criteria or objective function from here. In the drop-down menu, you have different options, including root mean squared error, Nash-Sutcliffe coefficient, and also correlation coefficient, but I recommend either Nash-Sutcliffe coefficient or root mean squared error. In both cases, here you decide about the number of simulations. Similar to Excel spreadsheet, you need to tell the model how many iterations you need. The default in Excel was 100. Here, the default is 50 so that you quickly get some results, but 50 for 10 parameters is not enough. Typically, you need thousands of iterations. Oh, you can experiment with this, but for large number of simulations, you have to be patient. Click on simulate, then you will get your results here, and you can use the plot function to plot your outputs, including all state variables and also river discharge. We completed our model, and we also used a simple optimization technique to adjust our parameters. Here we used our entire data for optimization and parameter estimation. In practice, we do calibration and validation, especially if we want to use our model for prediction outside our observations. We always set part of our historical data for validation. Let's say we put 30% aside and we use 70% of the data for parameter estimation. We do calibration as we did. Then we use the other 30% for validation. We go with the optimal set of parameters and we try to simulate flow in that 30% of the data, and we look at Nash-Sutcliffe coefficient and root mean square error. If Nash-Sutcliffe coefficient is reasonable outside my sample, it means the model is validated and it's a representative model. It is possible that you get really good performance metrics in 70% of your data in your calibration period, but poor performance in your validation period if you apply it to a different part of the data. In that case, it means the model is not really representative. It is good to simulate historical data, but it doesn't have predictive power. And there are many reasons for that in the literature, including overfitting. If you have too many parameters for that environment, or if your set of parameters are not generally representative. There is an ensemble-based version of the same model that does ensemble simulations. That means many different simulations that are equally good based on your own definition of what is good, what is acceptable. For example, you can get, instead of one simulation, 100 different discharge simulations, all of them with Nash-Cliff coefficient larger than 0.7. So instead of one set of outputs, you get many simulations, but they are all equally good. That allows you to investigate uncertainties associated with parameter estimation. We talk about that in the second paper here that focuses more on ensemble streamflow simulation. Both of these papers focus on hydrologic education. Finally, for those of you who are interested more in changing environments, we have another model designed for environments where one or more parameters change over time. For example, deforestation or land use, land cover change, or soil parameter changes can alter parameters over time. In the models we talked about so far, once we estimate the parameters, a parameter is constant throughout our time period. But what if, for example, our watershed goes through deforestation or there is significant land cover change? In that case, we may want to use varying parameters or a non-stationary parameter for that particular process. This is a relatively new area in hydrology. We have built a toolbox for you to explore this idea of changing parameters. For those of you who are interested, you can download it from my website or website of Dr. Mojtaba Sadeh. If you have any questions, you're welcome to reach out. You can also add your questions in the comments. I will try to answer all of them. Thank you.